All right. Oh, let's talk about what's happening today. I mentioned last week that I had a funeral today at 2. We're not going to do a lab. We're just basically going to do class till 1, at which point you will be set loose into the world to create beauty or whatever you want. So that's the plan for today. All right, physicists love conservation laws. Conservation momentum makes their hearts go all on Twitter. But conservation of kinetic energy, if I take the marker and I let go, it gains speed. Obviously, if it gains speed, it gains kinetic energy. But kinetic energy is not conserved, so we need to somehow deal with that. And they thought, well, let's see what's going on here. We got this object that's falling. I know there's a force acting on it, causing this change. So let's come up with a new type of energy based upon where it was. So kinetic energy is the energy of speed. So energy of speed. And so let's do one about where an object is, energy of position. Yes, Sushil.
Before you go on, for the last problem, so you have 343 joules equals to, or?
I did the squiggly lines meaning approximately equal to.
Okay, so how does that work? Like, because, like, aren't you, like, are we trying to find something else though? Like, or we already found?
We found the speed through the chapter 3 stuff that we did.
Okay.
And now we found the work done doing stuff that we just talked about.
Okay. So what's like the final answer for that?
All I was doing was just showing that the validity of this right here.
Oh, okay. That total work is equal to change in
Kinetic energy.
kinetic energy. And then also lastly, when you cancel out the initial 1/2 mp squared, why is it 0 again?
Because I had it starting at rest. The initial speed was 0.
Oh, okay. I see. Okay. That makes sense then.
Good. Other questions? Alright, so let's clear this stuff. So this new thing, position. Well, this is what they're going to call potential energy. Now some books will use the abbreviation of PE for potential energy and KE for kinetic energy, but that's just too much writing. So kinetic energy, capital K. So that makes some sense why they choose that. Potential energy, the symbol that's traditionally used, is a capital U. Sometimes capital V, but I do capital U. I think it's from the German, whatever the German word for potential is. Anyone here speak German? Okay. Then it's from the German. Now, potential energy, it turns out there are different formulas. So if I ever ask you what is the formula for potential energy, the right response is which one? So what's the formula for kinetic energy? 1/2 mv squared. What's the formula for potential energy? Which one? Because potential energy depends upon what kind of forces are acting on it. So there's a different formula depending upon that force. So if the force is gravitational force, and that's either Fg, F sub g, or the weight itself. then we're dealing with gravitational potential energy. And the formulas are either, for weight would be mgh, and for gravitational force, big G, and that's, I guess, the first time I talked about big G, mass 1, mass 2 over R. And I'll make an R. Negative. Now, hopefully on the second one here, the mgh, you recognize mg is weight. This is just weight times height. Oh, yeah, plus some constant. The constant we generally ignore. So the first one is just a weight times a height, so it's a weight times a distance. The other one might seem a little bit more obscure, and at this point, yeah, it is. I present it without any derivation whatsoever, because the derivation requires calculus. Another one that has a potential energy formula is ideal elastic force. I use an S for spring, it's like a spring force. And the potential energy formula for that is 1/2 lowercase k delta x squared, where this k is known as the spring constant. I'm going to do one more of these and then talk about what they have in common. Those are the two main ones that we would deal with in this course. If we probably not going to be enough time, but if we had enough time, there's also the electric force. If you've had chemistry, you've talked about positive and negative charges attracting, opposites attract. F sub E. This is why I don't use E for the elastic force, is because I use E for the electric force. And the potential energy formula is negative K sub C, Q1, Q2 over R. Looks a lot like that first one. Oop, not negative. Let's get rid of that. In this K sub C here is known as Coulomb's constant. Now, what do these have in common? In some sense, they're like natural forces, but that is a poor descriptor, but I'm going to come up with something that's really not a whole lot better than that. These are all conservative forces. And why are they called conservative forces? Because they conserve energy. It's as twisted as that. Now, if there are these things called conservative forces that conserve energy, what happens if you have something that doesn't conserve energy? For example, friction. What do you suppose that type of force is called? Someone take a shot at it. If it's not a conservative force, they decided not to go that route. They had less imagination. Non-conservative. So we have these non-conservative forces. So I don't need this anymore either. So this is U is potential energy. So non-conservative forces don't conserve energy. So if I look at these two things right here, I'm about to combine the two things. So if I have kinetic and potential, if I add them together, that gives me mechanical energy, which generally you just label as E, but you could also put a little subscript M down there. This is mechanical energy. One of the problems when Hewitt talks about what is the mechanical energy, and that's he's just saying you take the kinetic and add the potential to it. So if I take a change in kinetic plus the change in potential, I get the change in energy, mechanical energy. And so I'm going to bring up another one of these. If I'm looking at the non-conservative work, in other words, work done by non-conservative forces, that's going to be equal to the change in energy. Now, there are only two types of forces in this regard. There's conservative and non-conservative. Every force is going to fall into one of those two categories. There is a formal definition of conservative force, but we don't need to know that. Here's what you need to know for this course. That's the list. It's a gravitational force, elastic force, and if we get far enough, electric force. Anything beyond, other than that, assume it's non-conservative. So that means that, well, if I have only two types of force, that means my total work, well, it's got to be my non-conservative work plus my conservative work, because that's my only choice to take. Whatever work's done by conservative forces plus work done by non-conservative forces, that's my total work. So we can come up with a third relationship over there by, well, I know that non-conservative work is equal to the change in energy. My total work is equal to the change in kinetic energy. I know change in energy is just change in kinetic plus change in potential. That's delta K is equal to delta K plus delta U plus work conservative. If I subtract the change in kinetic energy from both sides, that disappears. Let's just bring this over. And so my conservative work is equal to the negative change in potential energy. Now, again, all of this I understand, a little bit abstract, just a bunch of letters, alphabet soup going on here. Let's point out what we have. These are the work-energy relationships. You're working on your dissertation, you're working on your Nobel Prize winning physics work, those are true. I'm going to do an aside in a moment, questions up to here. Okay, there is a third type of energy, known as rest energy. No, sorry. Keeping the pattern should be up here. So kinetic energy deals with it. The speed, potential energy is the energy of position, rest energy is the energy of mass. Now, most of you know the formula for rest energy, although if I asked right now what's the formula for rest energy, I suspect most of you would not know. But all I have to do is just say the first two words and you got the rest of it. Let's give it a shot. E equals, there's the formula, mc squared. I'm gonna make one small adjustment to that. Put a little sub-zero there, c squared. This is the rest mass. Every time that you have found a mass in lab, you're finding the rest mass. All right, we have rest energy you'll only deal with if you have something that bursts into flames or atomic bombs, things like that. That's when the rest energy makes its debut. If you strike a match and you get all of, little particles going to float up, if you capture all those particles and you find the mass of the burnt match plus all the little particles, that is not going to be the same mass as the match before you struck it. And that difference in the mass gets converted into thermal energy, or actually kinetic energy. Which brings in chemical energy is just potential. Thermal energy is just kinetic. There are a couple other catch-all terms that get thrown about in physics just because they don't feel like going into more detail, but it's going to fall into one of these three categories. And I think on that note, we have established all the groundwork. I think let's take a break, come back, and we will actually use this stuff. And then we will connect it, assuming we have enough time, to the stuff we did with momentum. So, stretch if you need to. All right, this is the problem we dealt with before. We know what the speed is. We found the speed using chapter 3 stuff. Now let's find the speed using chapter 7 stuff. So whenever you're doing one of these things, still starting out with the force diagram. What are all the forces acting on a ball that falls, being dropped, going to fall 7 meters? The forces acting on it. You need to refer to your notes. This would be under box falling. The checklist.
Weight.
Yep, got weight.
Normal force.
Pardon?
Normal force.
Normal force requires contact. It's just falling. We're ignoring air. Of course. So, other? Did I talk about no? All right. Tension? Friction? All right, so we have weight. Is this a conservative force or a non-conservative force?
Conservative.
Yeah, it's conservative. All right. So therefore, I'm going to start with this one right here. The non-conservative work is equal to the change in energy. So if the only force involved in this is a conservative force, how much non-conservative work is there?
0.
So 0 is equal to my final energy minus my initial energy. Because it's change, it's final minus initial. I'm just going to add initial over to the other side. E initial equals E final. This is conservation of energy. I have no non-conservative work being done. Energy is conserved. I have two types of energy. We're assuming this thing's not going to burst into flames. What are the two types of energy? They were written right up here. All right, so I have some initial kinetic plus some initial potential is equal to a final kinetic plus a final potential. What's the formula for kinetic energy?
1/2 mv squared.
Sounded like almost a single voice there. That's how in sync you were. What's the formula for potential energy?
1/2 mv squared.
Try that one again.
Okay.
What's the formula for potential energy?
Oh, potential.
That's the question. Yep.
Oh, yeah.
The one associated with that conservative force. MGH. So MGH initial is equal to, it's the same stuff except finals instead of initials. So that's 1/2 MV final squared plus MGH final. So I got kinetic formula, which all of you know by heart now. Oh, I did leave off a plus C there, plus C there. Now notice I did not write the plus C there, because whatever C is, it's gonna cancel out. I have the same thing on both sides, I can just subtract it, it goes away. I wanna figure out what that final speed is. Let's see, I know the mass. We'll go for the typical stunning visual effects here with multiple colors. I know mass, I know initial speed, I know mass, assume it takes place on Earth. I know G, I know mass. I'm trying to find that. I know mass, I know G. What are these pesky initial height and final height? What is the initial height?
Is this, 7 meters?
You said 7 meters? Okay, anyone else? We're gonna trust McKenna? Do we wanna go with what McKenna said? We got one person who wants to go with what you said. Okay, let's go with what she said. So the initial height is 7 meters. Why?
That's where it fell from.
Ooh, no, that's not why. I don't think you recognize how powerful she is.
That's right.
No.
Because that's what she said.
Yes.